Control devices, push button selector switches, joysticks, limit switches, daytime light switches, pressure switches, temperature switches, flow switches, gas sensors, liquid level switches, wind meters, automatic sensors, and then troubleshoot control devices. And there's a lot more than this, guys. So this is the makeup of a push button. So they normally have a legend plate on it. And what does that legend plate probably tell the operator? Yeah, what the switch does. And one or more contact blocks, which is most of your industrial switches, you can basically add almost as many contacts as you need. So this is this one. And we just stuck the contact blocks on here, by the way, so we wouldn't use them. There's a push button. Legend plate would go under the mount. This one, you won't run into these very often anymore because normally they put a shield around the outside of it. Then we just come up here and we screw these push buttons on here. On the left-hand side, we got all normally closed contacts. And over here, somehow we got a normally closed in the middle of a normally open, but they just stack on here. And then the operator, when you see you move the operator, it comes up here and it just daisy chains down through all your contact blocks. This is what's nice about a PLC. If we can do this in program controller, we'll have one push button, and then it's our program. We'll assign it to the same address. So we can have as many as we want. That would be the same contact block we put on there. Or we could do it one of two ways. We could let control it. So we got one contacts on it. So you're gonna have at least one contact block in there. But you could have one. You could have multiple. It all depends on the design. Some of them you buy you can't add multiple blocks. Some of them that you buy you can. It all depends on what they do at your company and what they want to do. It's nice doing this because what you do is you have one operator and then you got contacts, and then if one goes back, you just build the one that you need instead of having to buy what you need, right? So, but in a PLC, we use one contact, and our program says it has as many as we need. So that's another big advantage for PLC. So selector switches, an operator is a device that is pressed or rotated by the individual, which causes the contacts to change position. So all your normally open contacts, if you push that button, would swap up with open, and all your normally open contacts would close, and all your normally closed contacts would open. So when we're talking about normally open and normally closed contacts, it's if the operator is not being activated, right? Everybody understand that? So these are all selector switches except the one on the left, that's a push button. Contact blocks include normally open, normally closed. So like I said, some of them are fixed. Some of them you come up and you actually can add to them. It's got terminals on it somewhere where you can actually bring your conductors into the block itself. And then these are usually in some type of enclosure that'll help protect the connections from the environment. Contact blocks include normally open, normally closed, or both normally open, normally closed contacts, or multiple, right? So this right here would be a normally, this would be a, oh, that's one contact, one normally open, one normally closed, one normally closed, one normally open. So this would be a single pole, double throw, and then two normally closed, two normally open. This would be a double pole, double throw. And I think we've got that. Let's see, where's our systems? Right here. Double throws. So this one, you got one normally closed that you can't do anything about. Then you got two single pole double throws, which you can wire as normally. You can wire as normally open. Don't pay attention to the legend plate. All you're doing is looking for normally closed or normally open push buttons, right? So that right there, you can do a 3-input NOR or NAND circuit, or use it as a NOT, right? Use one of them as a NOT, or you could do two ANDs with that one station right there, because two of the push buttons are single double throws, which means in one position it's going to be closed, the other position it'll have like an open. So if you need a stop button, or you need a normally, so the first lab we're going to do, is we're going to check power. The next lab we'll do is we'll wire up the transformer up here. The first 3 labs, I think, are going to be homework labs. The next lab we'll do is we'll play around with the disconnect. And then after that, we'll start wiring up logic. And we're going to do two ANDs with 2 contacts. We're going to do ORs with 2 contacts. We're going to do NOTs. We're going to do ANDs with 2 contacts. We're going to be doing NOR. You can do every lab with that push button system. Because the only thing we're doing is 2 contacts at a time. If we needed 4 or something like that, we'd have to add another one, right? Understand that? So I'll come over there and somebody have this up there, and I'll have the other push button station up there. When they could have done it with that one right there. So when that comes around, you'll see, oops, we got one of these in that station, and then we got 2 of these. So double throws. So that push button station there is very cool. We okay? A push button station is what we're passing around there. It's an enclosure that protects the push buttons, kind of gives us some place to mount it, protects the wiring, and also protects the actual mechanics of the push button. So very seldom will you see the push button out there in nothing. It's usually going to be some type of enclosure that seals it up from the environment, right? You understand? It'll have holes coming into it that usually has rubber inserts or some type of compressor that you have to tighten down to keep the stuff from coming in where you make your connection. Okay. Wiring from dust, dirt, water, corrosive fluids, liquids, dirt, grease that we have all over the place out there. Selector switches, we already looked at this. This is 2-position selector switch. Our selector switch is the 3-positional selector switch. It's on the same block as your light. You texted in my class, Lila. Okay. So this is our selector switch here. It's a 3-position with a center off. So right now it's in the off position. And then they called it auto and manual, but one of them, if I put it in manual, then here's our diagram. If I put it in manual, then the bottom contact will close between 7 and 8. If y'all can see it, y'all can see it better. Between 7 and 8. And then if I put it in auto, then the contacts between 5 and 6 would close. If I put it in off position, then neither set of contacts are closed. So even though they're labeled auto and manual, you use the contacts. Like I said, these are just examples of legend plates, right? So we use it what we need to. They label this start, they label that start, but it's a light bulb, guys. If you need a light bulb, then you can use either what, the start or the stop. So our logic, this is what we're going to do, is we're going to turn on a light. We'll see the AND work, we'll see the OR work, we'll see the NAND, the NOT. And unfortunately, we don't do the exclusive ORs. I've been meant to add a lab on that. And by the way, don't write on my panels, right? You understand that? So hopefully that's in pencil. No, one of them's in ink. So this is not yours. I think it was right to use or something like that. These don't belong to you. That means any notes that's going to be on this would be done by me, right? You understand that? So I don't want to see any writing. Make your notes on your paper, make your notes on your lab. There's the selector. And the symbols vary. Like I said, US Steel uses a little different symbol than this. So the dashed line says if I put it in auto, this contact will here, and that the auto would be on the legend plate, right? It could be anything. It could be stop, start. It could be, grind to meet or something like that. But the legend plate basically tells what it does in the application that it's running in. The legend plate is replaceable. So I could have two exactly the same selector switches doing two different tasks, right? You understand? But each one of them will have the label for the application that they're doing. A legend plate, excuse me. So how does this circuit work? So I can switch between automatic, which would be go to the temp switch, or I can switch to manual, and then I would control the heater contactor with a manual switch. But what makes it auto and what makes it manual? No, I'm talking about what physically makes it auto and what physically makes it manual. It's who wires the dang thing up and who puts that legend plate, right? It should say two position select. Ours is a three position selector switch, right? You understand that? So what determines how it was, whoever wires the circuit up and bought it, okay, I need a two position let's just do a two position switch that does this. You don't buy an auto selector switch. You don't buy a manual selector switch. You buy a selector switch, and then you wire it to do what you want it to do, and then you put a legend plate up there that tells the operator what positions of the thing does, right? Does that make sense? Same switch, just has a different legend plate on it, and the contacts are labeled different. Three position, this is what we got. So if we put it in the center position, it moves to these dots, which means this contact is open and this contact's open. If I move it to manual, since they've got they got the solid one, it's going to close the top contact. If I put it in auto, which is the dash one, then it would close the what? Yeah, if I put it in auto, it would close this one and open that one. If I put it in manual, it'll close this one and open this one. If I put it in off, it'd be both of them. Both circuits would be open. Selector switch we got. Why did you need a selector switch that just had a manual on there? Well, you could use this switch. You just wouldn't hook anything up to the other positions, right? So later on, if we get that far, we do have one motor control circuit that we're going to make sure we do. We'll hook up a motor. We'll look it up directly first just to wire it for forward reverse. Then we'll hook it up to a manual motor starter, and then we'll hook it up to a magnetic motor starter. And then we'll come up later on and we'll hook it up to a reversing circuit, which changes somehow we electrically change the direction of the motor. So this is a select switch. This is a two-position select switch. What they gave us, and this is very popular with these, they'll come with the manufacturer's numbers on there, and then they'll come with a truth table that shows you if I put it in position 1, then circuit A is going to open. Circuit A will close and circuit B will open. If I put it in position 2, then circuit B will close and circuit A will open, whatever I have connected there. This is what you got. Because when they say a selector switch, they have no idea what you're going to use it for, right? So they don't say jog run, they don't say manual auto, they don't say light on, light off. What they do is they say, show you the truth table and say, whatever I have wired between A is going to respond, and whatever I have wired between the other will respond. Does that make sense? So do you understand the truth table? So this would be a center position. So the bottom one, if I put it in A, whatever I wire between A would close, right? If I put it in B, if I put it in C, then this would be a what? That would be off. That makes sense? This means that the one I wire between the A contacts would be true. This means the one I wire between the B contacts would be true. Are we okay? This makes sense? Okay. This is a joystick. This is a 4-position joystick. We have the truth table on the right. If I move to the right, circuit A would be true. The other 3 circuits would be open. Get to the left, and B will be true. Up would be C would be true. Down would be D would be true. Over here in the electrical diagram, they put a dot on it. See that? So if I move it to the right, then this circuit would be true. I need to be doing this. You'll see the dot? So this dot's on this side, this dot's on this side, this dot's here, and this dot's there. So what it's doing is showing us which circuit would be true in our actual circuit, depending on which position I put the joystick on. So the ABB robot's got a 6-position joystick on it. Sorry, 8-position joystick. It's not a robot that we have over there that's got a joystick on it. All the rest of them use push buttons. We okay? Yes? Limit switch. We're going to do labs with limit switches. I think I've already passed one of these around. This only detects in one position. We does in both directions. We have plunger type limit switches. This is a rotary type. So something up and hits that operator, it causes the contacts to switch positions. We had another one that had a yoke operator on it. I don't know if I can find it over here in this mess. Sometimes it operates in both directions. This guy here only operates in one direction. And it got the name originally when these things came out. That's what these things did. They did when something hit it. But now we use them for other things. We use them for count. We use them for when something's at a position, not at a limit. we use them, but it still has the name limit switch. This is a sensor. This is what we call a contact sensor. This is an electromechanical device, which means what? It means it can fail two different ways, which means these things can fail what? They can fail mechanically or they can fail electrically. The biggest problem we have is people don't fill them back up when they get in. So it's got to put a gasket around it, so when you put the cover on there, it seals it up. And then when you come in through the hole where the wire's got to come in, it's usually got what's that? That keeps it from getting goop in there, and you get guys out there that work on it, don't put the covers on right, or they don't put the clamps back on the cord coming in, and then goop gets in there and it starts getting in contact and mess them up. Another problem we have is people mount them wrong. They mount them closer than what they do. The operator, the guy that's trying to sense instead of the operator actually hits the limit switch. I've seen that happen a few times. So these are manually adjusted. You can't electronically set their sensitivity. You got to mount them right. You got to put them in the right place. You got to figure out how to do it. Keep it away from a lot of heat. I've seen these things at the top of a furnace, but all the heat from the door it just comes up, and we're replacing those things all the time. But could have put a little actuator on the side of the door to get it on the side. You would get to it, so it all depends on how you mount them. I think that actually gets that in your textbook. So these guys are still out there. They're all over the place. They're a lot cheaper than a lot of our solid state limit switches, and you'll see a combination of these. If I can get by with using one of these, I'll use one of these. If I can't, then I'll use something else. Like if it can't make contact, then I can't use a limit switch. The limit switch is what we call a contact sensor, non-contact sensors. They still have non-contact sensor going into the bookstore. Does this still buzz when you walk in there? Used to. Okay. So limit switches, these guys have their own name. All the rest of them, we call them proximity sensors and stuff like that with a category. This is in a category by itself because it was the first actual sensor we actually used. See how these things work? Like I said, two position, different operators. I don't know if I show you different operators in here or not. I mean, there's a lot of them. Now, how they normally we put this is the problem, guys. So here they're putting the load on the L1 side. Here they're putting the load on the here they're putting the load on the L2 side. So over here on this side, we got two pluses. Over here, and what they're saying is that if we get these contacts, yes, no. So if I call this L1 and I call this L2, then all your load should be where? On the L2 side. And what they're saying is it caused my contact. Here I have a plus. Here I have a plus. On the other side I have a plus. And on the other side I have a plus. So the contacts are not as likely to arc because I'm going from plus to plus and minus. Y'all understand that? Over here, what this person did is they wired this load on the L2 side. So here on this contact rear, I have a plus. On this contact down here, I have a what? A minus. So these are more likely to have the ability to arc between the contacts if they get too close together. That's what they're showing. So your control devices are where? Where do we connect our control devices? Between L1 and the load. Right? I mean, all our devices, all our contacts. So this would be somebody get fired for this. They ought to. It still don't mean you're not going to have welded contacts. It's just it's a lot less likely to do that, right? You understand? A relay contactor or motor starter must be used to interface limit switches to loads that exceeds the current rating. What's nice about these pilot duty or these bigger relays, a lot of times limit switches, a lot of times these guys can actually run loads. But we still are going to a water contacts rated in, by the way. So when I looked at the specs on this, it started talking about the contacts, water contacts rated in. Same thing that's used in the circuit breakers rated in. How much current the contacts can handle. Because these contacts, guys, are not, and they break, and they have a test point, right? How many contacts they can handle, and then what would be the second thing they're rated in. So voltage is a push. There's nothing out there in the world that has infinite resistance. So what happens is when we come up here and we break that push, then how much push that contact can break without it arcing over. So your contacts are going to be rated in a voltage, how much you can actually break. So you go out and look at a fuse. A fuse for a car is rated at 12 volts. You take the same fuse and you put it in your house, and you're trying to break 120 volts, and it could do what? It could arc across and cause problems. So anything that tries to break a circuit is going to be rated in how much voltage it can break and how much current we can put through it. So the more current the contacts are rated at, the bigger they're going to have to be, right? You understand that? Which means they're going to be expensive, they're going to cost more. So a lot of your motor starters, out of USD, I saw some contactors where the main contacts were as big as my arm. But these guys cost a lot of money, right? So fuses are rated at a current and a voltage. So the current is what would cause and circuit breakers are rated at a current and a voltage. The voltage means a guarantee that it'll be able to disconnect the circuit even though it's got to push there. So what we could do is we could have a limit switch picking up a control relay, and the control relay could run the load if it can do that. But we could also use a contactor, and the limit switch could energize the contactor, and the contactor we could actually get over into a power circuit, right? Understand? In fact, most of your limit switches now are little tiny things, because most of them now will input into a computer, and they don't conduct hardly any current at all. The operator, this is what actually makes physical contact with the device. We have different operators. So wobble stick, push roller. This would be this limit switch here can actually be changed from a rotary switch to a push roller by taking this output off. So a rotary limit switch does what? It actually rotates. The operator rotates the switch, where a push type would actually push it into it. Right? Does that make sense? Sometimes y'all gonna run it in. So some of the things, the degrees of operation. Does it contact in one direction or is it dual direction? How far you can cause this thing to deflect without it doing what? Without it messing it up. So limit switch is going to be ordered. Should not be operated beyond the manufacturer's recommended travel specifications. So if you got to replace a limit switch, then you need to buy one that's got the same. You don't necessarily have to buy from the same company. You just need to understand the specs so you know what you need to buy. Are we okay? CAM operated limit switches. We actually have one of these. Let me find it. This is called a cycle timer. And this could be just about any switch. So here's the actual limit switch right here, small one, right? And then this is the cam. And what it does is turns. It's got a little AC motor under here. I'll pass this around. And what it does, it turns the cam. And I think it's geared. I can't turn it. And notice it's got an adjustment on it, so we can actually adjust the gap here. This is called a cycle timer because it sits there and runs, and it creates a certain type. It's going to be on for a certain amount of time and off, and it's going to do just constantly switch between on and off and on and off. So this is the cam operated limit switch. This is the actual limit switch, and this right here would be the cam. Yeah, you can turn it if you turn it. It's hard. And like I said, this was the main use when they first came out. They literally sent position. But this, I mean, sense limits. This guy right here, this guy right here is. It's got a cylinder back there, and it looks like the limit switch is over travel. Well, cylinder cannot damage the limit switch. Oh yeah, that's just talking about how we mount them. So what do we do with limit switches? Limit switches we use to detect when something's at a certain spot, right? Does not necessarily have to be a limit. It could be just when something's at a position we need to be in. We have several of these on the manufacturing line. If you're in the PLC class, we'll probably get over there and look at those, but yeah, this is what we're talking about. Limit switches should be bounded to avoid accidental activation. Here they got one mounted under a lathe. Here's they got one mounted where at the top of the furnace instead of at the wall. Here they got it where it gets metal shavings in it. The top one, yeah, here they got a shield around it. I've seen that happen too, where people get in there trying to work on something and they actually accidentally activate the limit switch. I don't know. Foot switches. So foot switch, you'll see the symbol, right? So it's a basic symbol for a single pole, single throw switch, and then it's got a little hook. It's a foot switch. A lot of times they'll have a shield around it, a U-shaped shield over it, where people accidentally stepping on them. Are we okay here? Yes, no? This is what do they call it? You're not going to see them call this much anymore. It's also called a photoelectric. Huh? So these guys got lights. So the photoelectric sensor doesn't actually pick up light. Here they're using a photodiode. We don't use those much anymore. This assembles something called a photodiode. And of course, this is inside a diamond shape. If you take the sensors class, this is one of the sensors we'll do. This is a so this is a photoelectric sensor. It's a 3-wire sensor, which means it's got to be powered. And the how they came up with these color codes, I don't know. But the brown wire would go to L1, and the blue wire would go to L2, and then 2 would be the signal wire, and it's black, which gets us in trouble because normally over here we see a black wire, we think of it being common or L2 sign. So you can actually see the photo detector here. It's a 3-wire sensor. So notice what they did on in the book when they had a 3-wire sensor. They added a 3rd wire, which means this guy's got to be powered up to work. So this guy we don't want to power up through the load, and they got the color codes wrong. Oops. So this is a standard color code that we use now for these 3-wire sensors. The brown points toward L1. There can be something in here because it won't work until it gets through to it. So this guy has to be powered up to work. So, and where he came up with this color code, I don't remember that color code at all, but this is the ones that we use now. So we can look at any 3-wire sensor we got, and these are solid state, which means they'll never drop 0 volts. So anytime you see that diamond, it usually means it's a solid state sensor. There is one exception to the rule, but we'll talk about that when we get in there. So your low voltage inductive sensors are going to be 3-wire sensors. Those got sense metals. Your low voltage capacitive sensors, those got sense liquids and solids. That'll be used the same color code. Then photoelectric, I can bring out the temperature sensor, and it'll be a 3-wire sensor, same color code. I could bring out the pressure sensor, and it'd be the same color code. So this is standard color code that we use now. So in your book, I don't know how they came up. I don't ever remember seeing that. So brown goes toward L1. Blue does connect to L2, directly to L2. And then the black one, if it's an AC sensor, the brown and blue doesn't make any difference. But you need to follow an industry standard, right, to understand, because that way, if it was a DC sensor and you look at it backwards, you look at another one over here, it would go wrong. So AC, brown and blue wire makes no difference. But DC, if it's a DC sensor, it's very, very popular now. DC in control circuits is extremely popular because these guys are computers, electronic devices, they work off of DC. That means if I would have to go from DC, I have to go from AC to DC to run these things, right? You understand that? I mean, inside. So the inside and outside would be different. So DC, 24-volt DC is pretty much the standard for control circuits. First of all, it's below the 50-volt 70E standard, right? You understand that? And then they don't have to keep to DC and that kind of stuff. So we have one power supply. So here's the power supply right here. 24 volt. This sensor is passing around. That's an AC sensor. Runs off 120 volts AC. So what that means is you could literally put the brown, swap the brown and blue. Can't swap the black, but you can swap the brown and blue and it would still work. But this is the industry standard way. You need to do things according to industry standards, right? You understand? And we'll talk about that too when we get into some of our circuits that we connect. Pressure switch. These are not solid state pressure switches. We have a solid state pressure switch that we use, but it sense both what we call pressures and vacuums. Basically, a vacuum is any pressure that's below atmospheric pressure. What's standard atmospheric pressure? Anybody know? Surely y'all heard it. 14.7 close, yeah. Of course, that varies with altitude. It also varies with temperature. But that's the average pressure at sea level. So they took pressures all over the world, right? You know what I'm saying? It would, at sea level, it would average out 14.7. So that's usually what we consider. Okay. Okay. Oh my goodness. I would be too. The pressure switch we have is a dual pressure. So what it does is we can set a high level and a low level, kind of like a compressor. You've got a compressor in your house. It's got a pressure switch on it. It's got a high level and a low level pressure switch. That's one of the pieces of equipment that's paid for itself over and over again. Two things: my welder, my grinder, and my compressor. Those things pay for themselves over and over. And my miter saw. So I'll show you our pressure switch. It's actually digital. It's really cool. So a vacuum is technically a pressure. It's just any pressure that's below sea level is considered to be a vacuum. This guy measured both of them. What we can do here is we can actually set our limits. This is a 4-wire sensor, so it's got a white wire, which would be a normally closed contact. So the black represents a normally open contact. If we got a single low double throw, then the normally closed would be white. So we have 2-wire sensors. These are devices that actually power stuff through the load. These guys are using high voltage sensors, so where we can afford the drop. We have 3-wire sensors. These guys are usually operated at lower voltages, and you have to power them up. Right? You understand that? And we have what we call a 4-wire sensor. So black represents a normally closed contact. The black represents a normally open contact. If you got a 4-wire sensor, it's going to have a white wire represents a normally closed switch. If I said that right. So if you actually look in here behind here, you can see the brown, you can see the black. Now this is a 24-volt sensor, but the problem is that our control circuits are 120 volts. So what we do is we have a 24-volt transformer that we hook in here. And then what to do is the sensor, here's a sensor. and you can actually see the wire colors down there. This is what we use to program it right here. This is where we bring in our pressure or our vacuum right here. And what the sensor does is it brings in these control relays. And in the control relay, we put 120 volts across the contacts. Does that make sense? So what's nice about a relay is what controls the coil does not have to be what is being switched. Y'all understand that? So what we're doing is the sensor, we power it up all with 24 volts, but it's switching a 120 volt circuit. These up here that we have ways of pressure. Of course, the sensor's flat. What we do is we type some ways of pressure. This guy right here is actually using a diaphragm, but not this guy. So this is the diaphragm type. We got one of those up here. We have a bellows type. Now, normally, what we do is we have a physical sensor that actually detects the physical, and then we use something else to trigger electronics or the electrical. So this, I don't know what to do. This is a diaphragm sensor. So whatever we're going to measure the pressure, we put it in here. It causes the diaphragm to push back. That comes over here and causes this right here to move. And then normally we use a limit. We combine it with another sensor that actually senses it. So a lot of our sensors are actually two sensors that gives us one function. Just hold on for a second. This is a bellows pressure sensor. This guy can sense both a vacuum, so that means if we put a vacuum in it, it'll compress. If we put pressure on it, it'll do what? It'll expand. And then we add something else to it that actually would take the physical quantity it measures and converts it into an electrical signal. Then we got strain gauges. So these are just very few things that we have the ability to check pressure with. Piston, we don't have this one, but we have what we call a calibrated springs compress and extend at a precise pressure. It's just that normally springs are not made accurate, so that means you might buy two springs like on your pen, and you measure the compression length for one, you go to the next one, it might be different. What we call a calibrated spring, these guys are designed to actually expand and contract at precise distances with certain amounts of pressure or force. We use these a lot on scales. So if you go down to Walmart over there in the fruit section, they got a scale hanging from there. All you're doing is putting that weight on there, compressing a calibrated spring that compresses pretty precisely, right? You understand? Which causes an indicator that moves. They call that. Shots, but they're probably not calibrated. But they would compress a certain amount depending on the weight. But every one of them on a car, it would be very expensive to get exactly the right compression. Understand what I mean? So one of them, you put 2,000 pounds on it, it might compress maybe a quarter inch. The other one might compress a half inch, but it's not going to be enough for us in a car to know the difference. But it would be awful buying and selling something that didn't give us the exact same compression or extension. So yeah, shocks are nothing but springs. So what happens on these piston types, we come up here, we put a pressure in here, it hits a surface, generates a force. The amount of force it generates would be proportional to the pressure. Then it pushes against the spring, and then where the spring stops, where it matches, right? You understand? Then that's where it would stop. Piston types, bellows types, diaphragm types. We use strain gauges. We use all different types of things depending on what you do. But all these guys, it takes a pressure, converts it into a force. So basically, we're technically measuring force. What's the difference between pressure and a force? So a force is actually motion, right? You understand that? So we can't get in the formula, for force. Close, but you're going the wrong way. No, pressure, speed is determined by how fast the flow is moving, right? But forces is determined as how much pressure you have and how much area you're pushing that pressure against. And a force is anything that causes or tends to cause something to change direction. So if I come over here and push against this wall, then we're generating a force, but we're not getting any work. To get work, you got to actually make something move, right? So normally, this is what these things work with. We have a pressure, we push it against an area, which causes a force, which causes something to move, and then we measure how far it moves, and that would give us that would be, if we can measure how far it moves, that would give us a pressure. If we just say, okay, it's going to get to a certain point to trigger, so like your compressor, your pressure sensor on your compressor, when it gets below 70, around 70 psi, it does what? Turns it on, right? Not at 70, around. And if it gets above 100, it usually does what? Cuts it off. So, and those guys are just looking for a sensor to move a certain distance for those different pressures. But it's probably operating, those are probably operating against a what? Against a spring, a calibrated spring. And this is exactly what they're talking about. Deadband is a range of pressures that the thing would go between. So when you're operating between 70 psi and 100 psi, we call that would be what they call the deadband, right? That's between your upper limit and your lower limit. So once you hit 100 psi, around there, what happens to the motor? Cuts off, and then you're out there using your tools and stuff like that. And then, so compressors are rated at two different things. What's the two things we rate compressors at? Feet per minute, CFM, and that gives you the flow rate that how fast things are going to move. So how fast the fluid moves determines the speed. The pressure determines the force. See, I want to know about that. And it's usually SCF. It's usually standard cubic feet per minute, SCFM, because the flow rate varies with that amplitude. So the higher you get, the flow rate would be different. So that's usually at sea level. Was that me or somebody else? Yeah, we're fixing to. Pressure switches determine pressure tank. Pressure determines pressure. We can have pressure without a force, but we can't have force without a pressure, right? Does that make sense? Heat sensors, everybody okay there? You understand those? These things work. We have several principles these things work at. These are temperature switches. Everybody know the symbols, right? So what's the symbol for a pressure switch? Everybody okay there? Sensor symbol for a temperature switch. Now, why is learning symbols important? Yeah, that's what we're talking about. So you wouldn't be able to read the drawing if you don't know the symbols. It's a temp switch. It's temperature switch. We got these in our HVA system. I mean, they're. I got a temp switch here that came out of my air conditioning unit. First one. So my house is paid for. So I'm on my second air conditioning unit, or maybe my third. So usually when they come out and get them, I go out and rip them for parts so that I can show and tell them to my class. I really want to go to lab next class, guys. So y'all need to really, huh? Well, some of y'all don't have y'all's lab book yet. This is a temperature sensor called an RDT, which is a resistive temperature device. What determines the resistance of a conductor? Close. Keep going. 3 things. 4 things, I'm sorry. Yeah, that's the last one we're looking at. So material, size, length, and then temperature. So we have a sensor called an RDT, which is a resistive temperature device. And that's this guy right here. So it's nothing but a bunch of coils of wire. That's this guy right here. It's an RDT. So this would give us an analog signal. This guy at the end that's bent up, this is a bimetallic temperature sensor. So it operates a switch. There's a switch back here in the back, but it's been bent. And bimetallic just warps with heat. So this has both bimetallic and a RDT temperature sensor in it. And so I have a called a combo unit. So I have gas heat and I have electric air. That was actually mounted into the firebox that where the combustion actually takes place. So the top one would have this symbol right there. The switch would have that one. Yeah, we're fixing to get out here. We'll look at these. We'll start off lecture. Hopefully y'all can get y'all's lab books. We'll do some homework labs. I'll tell you the homework labs that they'll be. I'll give y'all the lab procedures next class. I'll show you about the lab forms. I'll come up and I'll give you, let me think. And we're going to try, like I said, the first 3 labs are like our homework labs. So I think one of them safety, one of them standard equipment and stuff like that. One of them we've already done, right? We did the lab for our kids. I don't know. They don't. I don't know. You need to ask them. They might have some in the back. Yeah. And if not, we really need to get some back in here. This bookstore, I am not impressed.